All right, last three problems, almost done. 10 says give the reagent needed for each of the conversions below, A, B, C, D, E, and F. So we're going to wind up with a reagent for each, A, B, C, D, E, and F. A, you are taking this, there's two alcohols on a hexene ring or hexane ring, so it's a diol, but A wants you to oxidize both of these alcohols. This alcohol right here all the way to a ketone. This alcohol past the aldehyde step all the way to a carboxylic acid. And so you need a really strong oxidizer for that, and Jones reagent is the reagent of choice. On the Grinnard notes page that I sent out, on the page that starts with Grinnard reagents continued, in the bottom right hand corner I wrote a little quip about Jones reagent, but when you see the answers that he posted as CrO3, that chromate, or Na2Cr2O7 or K2Cr2O7 plus H2O plus H2SO4, you are like what that's known as is Jones reagent, and you're forming this guy right here. You're forming that so that you can form CrO3. Anyway, check out those notes for a more detailed explanation, but Jones reagent is a strong oxidizer, and it will oxidize an alcohol to an aldehyde, and then it will continue oxidizing it to a carboxylic acid, which is what you want there. So B says that it wants you to oxidize this alcohol into a ketone, but it wants you to leave this as a aldehyde. And in the last video I said PCC, and I drew out what it is. It will oxidize a alcohol into an aldehyde, which is what this group is, but it will not take it one step further into a carboxylic acid. So PCC is the reagent of choice. For C, you've got this ketone group with this alkene group, and it shows it kind of reducing the ketone group. So anyway, H2PDC, we learned in Organic 1. We'll take that carbon-carbon double bond and add two hydrogens to it, and kind of split it apart. So the kicker is that you want to leave this ketone group on, so it needs to be at low pressures. And because the H2PDC at high pressure, it will also reduce this this ketone group down to an alcohol. So in D, it shows you reducing the ketone group to an alcohol without touching the carbon-carbon double bond. And so we've been talking about for a couple weeks now NaBH4, sodium borohydride, and lithium aluminium hydride, and those are both reducing agents. But they're kind of more selective for carbonyl groups. They're not going to reduce the carbon-carbon double bonds. And so just make sure that you follow those up in so anyway, sorry, I don't know what my next thought was there. E shows you reducing both double bonds, and like I just mentioned, H2PDC and high pressure will do just that. And then F shows you reducing that carbonyl carbon to an alcohol, but it also has you adding that doohickey, and so that's kind of the classic thing. You're adding a carbon group on there, so you want a Grinnard, and in this case it's going to look something like this. So that is number 10. Number 11 here says draw the final major organic product for the reaction sequence below. I thought it's this reaction sequence right here. I thought this was pretty clever. I kind of hadn't thought about this as a possibility, so I'll go through it with you. Cl, and you're kind of doing this number in AlCl3, which is going to form. The AlCl3 is going to cleave off this the chloride on the acyl chloride, and so just like it would in a Friedel-Crafts. And so you're going to have a positive charge there. I think that positive charge then, as he shows it, goes and electrophilically attacks the benzene ring and does a kind of a ring closing mechanism there. And so it would look like this. And it's really, really important here to count your carbons as you close a ring, because it's really easy to lose or throw in an extra carbon. And in this reaction, there are no extra carbons coming into play here. It's just closing the ring. So make sure you count your carbons. I'm going to say I got 1, 2, 3, 4. So I'm going to have 1, 2, 3, 4. And then that'll close my ring. So I've got 1, 2, 3, 4. 1, 2, 3, 4. So I can do this number right here. And then you are going to do the Grignard step. And so that is going to, you're going to do a nucleophilic attack on this carbon with the methyl group, and so it's going to come down and form this. Of course, I mean, you gotta follow it with a aqueous workup there. And then you've got this methyl group that came from your Grignard. So, I mean, hopefully you can tell that's methyl. We'll get to it in a second. And then you're bringing an acid into the equation. So that acid right there is going to kind of add on to this, and then this whole structure is going to come off as water, leaving you with a positive charge right there, and it's going to form an elimination reaction. So let me not show that in that step. I'll show it in the product here. Forgot about that guy. Remember, the oxygen's gone now, so we have that methyl group, and then the H, one of the hydrogens from this carbon, participated in this elimination to form this product. So, man, that problem has several neat things in the idea of the chloride leaving and a ring closing occurring, and then the Grignard addition, and then the thought of cleaving off that water with the proton such that it forms an elimination reaction. I don't know, just kind of a lot of cool things happening in that one. And then last of all, give the mechanism for the reaction below, and gosh darn it if this isn't another Grignard. So because it asks, I would kind of skip the mechanism and just show the product, but because the point of this problem is to give the mechanism, I will run through it. I want you to start with this ester. I'll put a CH3 there, and I'm gonna show these split for this sake. The methyl group here, the methyl group of the Grignard reagent, is going to be the nucleophile, and it's going to attack right there, that carbonyl carbon, and it's going to form that tetrahedral intermediate where the electrons get pushed up to this oxygen, giving it a negative charge. You got the CH3 on there. You got the O right here, CH3, and so right here, because this oxygen is a good leaving group, it's going to take off as these electrons push down to form that kind of stable carbonyl double bond structure again. So now you have this situation where that oxygen is neutral again because it's carbon, or I did one extra electron. Yeah, this is neutral again because its electrons came back down to this carbon. We've still got this methyl group, and then this group kind of cleaved off, and it took these electrons with them. So I guess I better show that it looks like this at this point. So it's gone now. We are going to bring another Grignard nucleophile in here. And it's going to attack that carbonyl carbon again, doing kind of the same thing. But at this point, where it'll be different is that you got CH3, CH3. Now you've got that O minus right here because it's got those extra electrons kicked up to it. At this point, neither of these carbon groups are good leaving groups, and so you have to, in order to get rid of this negative charge, you do an aqueous workup and add an H, and the H adds on there to form this final product right here. Sorry, I know this benzene ring is sloppy, but I think you get the point. And so anyway, yeah, this is the reaction. Hey, so I restarted this because as I looked down at Dr. Nan's answer, he highlighted another part of this reaction that I just want to clear up. So so in this part where you have I'll kind of show a water molecule here. You have these electrons pulling a proton off, and so you're left with this negatively charged OH group, and that negatively charged OH group right here, let me kind of circle this in a different color so it's clear. This negatively charged OH group links up with the original positively charged aspect of that Grignard reagent. And again, that mechanism is in the notes. I went over it in the last video. You end up with, like in a Grignard reagent, the MgBr is the positive part, the CH3 is the negative part. So the positive aspect of this MgBr links up with the negative OH group to form MgBr OH. And so that's, if you look at his explanation, that's where the MgBr OH comes from. So I wanted to make sure to include that. So anyway, with that, I think we're done.